Hi, everyone. My name is Melinda Meringue, and this is my colleague, Dilesh Manloy. We're product engineers on the Network Analyst team, and today we're going to talk about how to solve large network analysis problems with Python. This presentation is going to go kind of fast, and we have a lot of code to show. So this URL is where you can go and download the code and the slides. We'll show it again at the end, but go ahead and take a moment to take your photos. All right, if you missed that, we're going to show it again at the end. So before I get too far into this presentation, I should note that the Network Analyst extension is about solving transportation problems. If you're here to learn about utility networks or streams or something like that, you're in the wrong place. We do get that sometimes. So Network Analyst, we have different tools for solving problems having to do with assessing the coverage of different facilities, for optimizing site selection or the routing fleets of vehicles, and then we have various tools for point-to-point routing, including the route solver, the closest facility solver, and the OD origin destination or OD cost matrix solver. So what is a large problem? Well, a large network analysis problem is typically one that can't be solved in one calculation, just because you have memory limits. There's maybe if you're trying to use a service, the service has particular limits as to the number of things you can pass into it. Or even if you could try to solve it in one go, it would just take too long and you don't want to wait that long. So a large problem might have a large number of inputs, or maybe the number of outputs are really large. So for example, the OD cost matrix tool, if you have a bunch of origins, the output is going to be the number of origins times the number of destinations, which starts to get really huge. So 1,000 by 1,000 doesn't sound that big until you realize that yields 1 million records in the output. So an example of a large problem could be that you want to calculate the drive time for all patients to the whatever medical clinics are within, say, 100 miles of those patients. Or maybe you need to calculate the network distance from every parcel to every other parcel in a city as input for something else. So those could become large problems. So today we're mostly going to be focusing on the OD cost matrix tool, but a lot of the lessons that we're going to learn will apply to the other network analyst solvers as well. So today's goal is to construct a script that can solve an OD cost matrix problem of arbitrary size, so any number of origins and any number of destinations, using either local data or a service, and with or without a time or distance limit. And we want to then combine the output into a single feature class. So as a reminder, the network analyst workflow using local data kind of involves 4 steps. The first thing you have to do is to make your analysis layer. So in this case, we would make an origin destination cost matrix layer. That kind of configures the properties, and it's like an empty bucket where you're going to put the data. The next step is to actually add locations into that NA layer. So you need to add, if you have a point feature class of origins and a point feature class of destinations, you need to actually add that into the NA layer. Then you solve the problem, and then finally you retrieve the results and work with it. Now if you're using a service, it's a little bit more simple. All you have to do basically is you call the service and pass in all of the inputs and the parameters you want to use, and then you retrieve the results from the service and work with them. So what are some things you can do to optimize solving a large problem? Well, the first thing to do is to try to reduce the problem size if possible. Then you can chunk up your data if you still need to. Spatially sorting that data can help you out. And then once you've got your chunks, you can solve in parallel. And then a couple of network-related things you can do as an added bonus are to pre-calculate the network location fields and then use a network dataset layer instead of a catalog path to a network dataset. So I'm going to go through each one of these in more detail, and then Dilesh is going to show you an example in the code that walks you through all of these things. So the first thing that you could try to do is to reduce the problem size. If you're going to calculate an origin destination cost matrix, do you really need to know the travel time from every single origin to every single destination? Or can you make it a smaller problem? Do you need maybe only things that are within some kind of a time or distance limit? So I want to know the travel time to everything that's within 100 miles. because that will drastically cut down the problem if you can kind of fence around each origin. Or do you just need the k nearest destinations? So maybe I only need to find the closest 5 clinics to my patient rather than every clinic. You know, if my patient lives in California, I probably don't need to find the clinics in Maine. So another thing you can do is, if you are looking at a travel time limit, you can still use the select by location tool to find everything that's within, say, a straight line distance. So if you're using network distance as a cutoff, you know that the straight line distance is always going to be greater than or equal to the network distance of something. So you can first just select the destinations that are within some safe straight line buffer before you calculate the network distance. And if you're using travel time, you kind of have to do a little bit of an estimation. So you could say, probably no one's going to be driving more than, say, 100 miles an hour. So if my time limit is an hour, then if I use 100 miles, that's a pretty safe buffer in which you can select the relevant destinations. So that's a good way that you can cut down that problem size and make it more manageable. So then once you've cut down the problem as much as you can chunk up your data. So you'd want to break up the origins and destinations into chunks of a reasonable size. How do you determine what size is reasonable? Well, it kind of depends on your memory limits or your service limits, and that's really going to depend on your own machine. But just remember that the result of an origin destination cost matrix is the number of origins times the number of destinations. So consider how much output you can hold in memory when you're considering your chunk size. So when you've got your chunks, then you can iteratively solve the problem against each of these chunks and then combine the result in the end. So in order to optimize the chunks that you're using, spatially sorting the data can help a lot. And to spatially sort data, you can use the sort geoprocessing tool using the shape field as the sort field. And you can use the piano curve option to kind of make these nice, convenient little clumps and clusters as it goes through. One thing to note about this is that the sort tool, if you're using the shape field, requires the advanced license. So if you don't have the advanced license, you won't be able to do that. So let me just illustrate the chunking and sorting. So here's 26 million origins, that's all the purple dots, and then about 220,000 destinations, that's the orange squares. And so this is clearly too large for me to do in one solve. So how am I going to chunk this? Well, say I just select 1,000 unsorted origins. It's just kind of a random smattering of origins across the country. And then if I want to chunk up the destinations, let's say I want to reduce the problem size by picking only the destinations that are within 100 miles of these 1,000 origins that I've selected. Well, here I've selected all the destinations that are within 100 miles, and it's about 98% of the destinations data set. So then, of course, if I wanted to solve it this way, I would really have to go through a lot of iterations of solving because I can't pass in this many destinations all at once. On the other hand, let's say I spatially sort my origins, and then I select 1,000 of them. So here, this is that tiny little purple dot down in the corner. That's 1,000 origins that I've just selected right here in Palm Springs, and they're all clumped together. So now, if I select all of the destinations that are within 100 miles of those sorted origins, now I've selected only about 3% of those destinations, and I don't even need to worry about the rest of them for this chunk of origins because they're just not even relevant for my problem. So this way, you can really cut down on the number of iterations that you're going to need to do. So once you've got your chunks figured out, you can solve in parallel. The concurrent futures module in Python makes this particularly easy. And you kind of have two options with that. There's multiprocessing and there's multi-threading. Multiprocessing is probably going to be what you want to use. That's probably the best choice for this. The reason is that multi-threading just doesn't work too well. It's not good for CPU-intensive problems. And ArcPy itself doesn't really work in multiple threads at the same time. And so you would only use multi-threading if you were not using ArcPy, or if you're because you're calling a service, for example, or if you're writing a script tool that's intended to run within the app. So inside ArcGIS Pro, you can't run multiple processes at the same time. Another thing to watch out for with multiprocessing is that you can't write to the same geodatabase from multiple processes at once, and you can't share a network analyst layer across multiple processes. So you have to figure out how to make your code not do that, and just like per process do your writing, and then when you combine the results at the end, you can make them all merge back together. So Delesh's code is going to have some examples of that. So a couple of network analyst specific things you can do. Pre-calculating your location fields can speed things up a bit. So what are location fields? Location fields define how each point snaps to the network data set. So if I have a latitude longitude point, it's probably just kind of floating out in space, and it's not necessarily spatially coincident with my network itself. And when you run the add locations tool in Network Analyst, that will determine where on the network data set those points should snap to, and that snap location is considered the starting place of the analysis. And so if you're chunking up your data and you have to pass the same chunk of origins or destinations multiple times because you have to be able to run it through all the different chunks, it's not very efficient to have to calculate those location fields every time. So you can use the calculate locations tool to pre-calculate those location fields in advance. And then when you run add locations, you can use field mapping to just say, hey, use these location fields that I already calculated rather than doing it again. And that will save you some processing time. And then finally, there might be some performance improvement if you use a network dataset layer, because opening a network dataset from a catalog path can be slow, particularly if that catalog path is a licensed network dataset or if it's on a UNC path. So the make network dataset layer tool allows you to sort of read in that network analyst network dataset. It doesn't read the dataset into memory, but it reads the connection to that into memory. And then if you can just pass the layer into various things where you're going to be using it, that's more efficient than using the catalog path to disk. All right, so Delesh is about to show you some code, and here's an outline of what we're going to have in it. So again, the goal is to solve an OD cost matrix of any size using either local data or a service, and write out the results to a single feature class. So the code has a couple of different components. First, it does some pre-processing. So we're going to show that spatial sorting and also calculating those network location fields. Then we'll solve the problem by chunking it up and solving in parallel. And then finally, we'll post-process the results by merging them all into one feature class. So, Delesh?
Yeah, it's fine. Thanks, Melinda. So let's look at the tool that Melinda was talking about and see how we go about solving large problems and actually implement them in code. So you are going to get this source code file. It's a single file with about 600 lines of code. So I cannot really do justice and explain all of that in 10 minutes, but I'm going to give you the most important parts. So when you look at it on your own, you can figure out what's happening and what's going on. Now first, in order to run this tool, it's a command line tool with its own interface. So this is the function where we define the interface for the tool, and it just takes different options as inputs. So essentially what it's taking is it's taking the origins feature class, the destinations feature class, the full catalog path to your network data set or the URL to it, the number of the travel mode you want to use, the folder where you want to write the outputs, the cutoff and the number of destinations you want to find, the number of parallel processes that should be used, and the maximum OD size. That is the limit that you might have determined based on your memory or machine requirements. The tool has the documentation for it, so you can just run it on the command line with the -H option, and it will print all these parameters that you have. So that's the interface. Let's get that out of our way. So once the tool is invoked, it calls the main function, which essentially calls these other two, this wrapper function and the class. So let's look at the main function. So here we are first creating the output workspace in the output folder. So this is the folder. Can everyone see the code behind, or I should increase the size? Okay, good. So I'm first creating the output workspace here, and this is where I will store my eventual output, that is the single feature class that has my origin, destination, cost matrix. Once I have created the workspace, I am now pre-processing my inputs. So let's look at what happens when I am let me just fix this so I can check. Okay. So when I am pre-processing, can people hear me? Fine. Okay. So for pre-processing my inputs, let's try this thing again. Okay, so in pre-process inputs, we take the input feature, which could be your origins or your destination, your source, the travel network data source, the travel mode, and the output workspace. And the first call we are doing here is to actually spatially sort. So we are running the sort tool in this line and using the piano curve option that Melinda was describing. Once we have done this, if our network data set is pointing to a catalog path, we are actually calculating the network location fields by using the calculate locations tool. If it's a service, the services don't honor this location field, so we are not calculating this. So that's our pre-processing out of our way. So let's get back to our main function. Once we have done our pre-processing, we need to start the chunking process. So in order to help us chunk, we are first getting the counts of origins and destinations. We want to know how many origins and destinations we have. And then we pass that count and the maximum size that we can keep in memory to this function called get OID ranges. So let me get to that. Okay, so this get OID ranges, it takes the counts and the max OD size, and essentially it's going to return the ranges of OIDs, object IDs, that should be processed in a given iteration. So let's say an example here is if you had 200 origins and 100 destinations and your max size was 10,000, then this function would return an iterable where you say, okay, for first chunk, process the first 100 origins with the first 100 destinations, then take the next 100 origins and process them with the first 100 destinations. Here the function tries to include all the destinations if it can, and then tries to chunk the origins. Now why this is important? Because the OD cost matrix calculates faster if all of your destinations are in the single problem. So whenever you're trying to break up, make sure you try to include all the destinations and then break up your origins, which is what this function is doing. So it's generating that kind of iterator and returning it back. So now we are here, we got our ranges or our iterables. Now we are doing this OD cost matrix process on multiple processes. So to do that, we are using the process pool executor, as Melinda pointed out, and to that pool executor, we are initializing that with the max workers. Max workers is how many parallel processes you want. In this case, we are getting that as an input from the command line. So it could be 2, it could be 4, depending on number of CPUs that you have on your machine. Once we get the process pool executor, we are using the map function on that executor, and to that map function you need to pass two things. One is the function that should execute and the iterables that should be used for each iteration. So what we are saying in this line of code here is, on each process, take this solve OD cost matrix function, which we will look into what that function is doing, and for every iteration pass the elements from the iterable that you have created. So in this will in effect do like take the first 100 origins, first 100 destinations, call this function on one process. On a parallel process, take the next 100 origins, the first 100 destinations, and start processing them. So this is what it is doing and collecting everything back into the result. So now let's look at what this function actually is doing. Okay, so this solve OD cost matrix is essentially a wrapper function which calls this OD matrix class which is doing all the heavy lifting. So let's look at this function pretty quickly. So it's first initializing the class, the OD cost matrix class, and in the constructor of the class, what we do is we set up all the inputs. Now here in these lines, we are creating a unique workspace per process. Remember, Melinda talked about you cannot write to the same file GDB from different processes. So what we are doing is we are just essentially creating a unique ID, and then we are creating a folder based on that unique ID. We are creating that folder here based on that unique ID that we got, and then we are creating a file geodatabase in that unique folder. So every process gets a unique folder and gets a file geodatabase in that folder, so it can start writing to that, and there is no contention with other processes that are writing to some other folders. So that's how we achieve, that's what we achieve in the constructor. We also create a network dataset layer. So what we do is in this function here, make network dataset layer, we say if it's a service, we cannot create a layer because you can create a layer only on a local network dataset. But if the layer already exists, we just say return because the layer has been there. If it does not exist, we use the catalog path and create the layer. So first time when the process is launched, it will create a layer, but next time when that process is processing a job, it will just use the layer that was previously created and would save up time on actually opening up that network dataset. So back to our constructor functions, here we are just setting up certain inputs that we need to use later on. So that was the constructor function. Back to the service now, then we are figuring out whether it's a remote service or it's a local, whether we are executing against a local network dataset or against a remote service. So we'll look into those two functions. Let's first start with the local function. So this is the local OD solve. Now this is following that 4-step process which Melinda determined or outlined. So this, we are first checking out the network analyst extension license. We are setting the workspace to the workspace that we had created in the constructor. Then we are creating the new OD cost matrix layer. We are getting the sub layers. We are selecting the inputs. So this is where we are doing, we are getting the chunks, that is the OID ranges, and then based on those OID ranges, we are creating layers, passing in those OID ranges to construct a where clause. If we have a cutoff, we are doing a select layer by location so that we only select destinations that are within that cutoff. And one thing to note here is this piece of code which is saying when you run select layer by location and there is nothing within the cutoff, it will actually do no selection on your layer. So we are checking for if we got any selection, and if we didn't get any selection, there are no destinations that are within the cutoff, so there is no point in doing that iteration and we just return the error out. So that's the selecting the input parts. Once we have selected the inputs, we load those inputs into our NA layer, and when loading the inputs, we are mapping the object ID from the inputs into the, as the name field into the origins and the destination sublayers. We are using add locations to load them, and we are also using the location fields that we have calculated using the calculate locations tool. Where we are using the location fields, this field mappings, the boolean here says to use location fields, and then our input has the location fields, and that's how the analysis knows to use those location fields. We are doing a solve here. If the solve is successful, we save out the results to a layer file. So if we have to analyze it, we can analyze that part, or we take the sub layers, transfer the OIDs, because we want to make sure our output OD lines have the object IDs from the input origins and destinations, and then we export those results out to a feature class on disk. So that's what is happening per process when we are doing the local execution. Now if we are working against a service, this is the function that actually performs the same analysis against the service. Again, it's selecting the inputs, so it's doing the exact same way. To work against the service, I'm using the Python API, which ships with ArcGIS Pro 2.1 or later. And using the Python API, I am first creating a GIS instance, passing in this magic keyword pro. What this does is, it uses whatever authentication was used in ArcGIS Pro to sign into your portal. So that way your code doesn't have to worry about authentication at all. It's delegating all the authentication to Pro, and that way you don't have to say take in username and password and worry about how can I store that securely and so on. You delegate that to Pro and let the user sign into their portal into Pro and then run this tool, and it will use whatever the credentials were there in Pro. So I'm initializing that, selecting my inputs. Then I am within the Python API, you can call the origin destination cost matrix service from the network module. I am calling that, passing in my inputs to that service, and I am checking for the result. If it's successful, I am saving the results to an output feature class. So that's the local versus remote execution. So back to our wrapper function, we are doing the calls, and then that this function gets the result object and passes that on to the main function. So now we have solved our results. So we are saying for each result, check if the solve was successful. If it was successful, append the or add the feature class that was stored for that process to an array of feature classes. So here I am creating an empty list, and this is essentially output from each process. So I'm saying get the output from the first process and make a reference to it so that I can later merge this thing together into a single feature class. So this array is, or this list is being populated here for each result object, and then once I have merged everything, I am combining that into a single feature class by calling the merge tool. So, and then I'm doing the cleanup because I want to make sure all the intermediate results are being cleaned out. So that's essentially how it is doing divide and conquer. Break it up into multiple parts, solve individual parts, and then combine them together, you get the result that you want. Back to you, Malina.
Thanks, Dilesh. So we realized that that was a lot of code that was thrown at you and that you probably couldn't follow all of that completely. So again, there's a download link where you can go and get the code. It should have comments, and there's a README that says what to do with it, and all these slides are there as well. So just to recap, things that you can do to solve a large problem with Network Analyst. First, reduce the problem size. Chunk your data, spatially sort your data, solve in parallel. Also, pre-calculate your network location fields and use a network dataset layer instead of a catalog path. So with that, we'll take questions. Here, I'll put that back up.
And one thing, the showcase here closes at 4:30 today. It's not open tomorrow. So if you have to get hold of someone, talk to someone, please do that today. It will not be open tomorrow. So make sure you get your questions answered today and leave the sessions that you have to attend for tomorrow. The sessions will be there tomorrow, the showcase will not be. Yeah, thanks all, thanks everyone, and have a great conference.